Hello dear student, welcome in KRT Arts, BH Commerce and AM Science College, Nasik, Department of Chemistry. Student, myself V.S. Shinde. In previous lecture, we have seen HSAB principle, that is hard soft acid base principle, some concept related with HSAB principle, its different types of examples and application of HSAB principle. Okay, in today's lecture, we will discuss basic concepts of stability and liability. Okay, student, so let's see first learning objectives for today's lecture. So first is stability of complexes. After that, we have to cover thermodynamic stability. Next, kinetic stability. After that, labile and inert complexes. And last one, we have to cover stability constant. So, in today's lecture, we have to cover all these points, that is stability of complexes, thermodynamic stability, kinetic stability, inert and labile complexes, and last one is stability constant. So, student, let's see first stability. So, the quality of substance which describes its behavior in chemical reaction in studying coordinate complexes. What is stability? The quality of substance which describes its behavior in chemical reaction in studying coordinate complexes. Basically, in solution, there are two types of stability. First is thermodynamic stability and another one is kinetic stability. In solution, there are two types of stability. First is thermodynamic stability and second one is kinetic stability. So let's see first thermodynamic stability. The thermodynamic stability and kinetic stability are somewhat theoretical, but it is easiest one. So this type of stability deals with the properties like bond energies, stability constant and redox potential that affects the equilibrium condition. It measures of extent to which the complex will be formed or will be transformed into another species when the system has reached equilibrium. Okay, I again repeat. It measure of extent to which the complex will be formed or will be transformed into another species when the system has reached equilibrium. It is related to spontaneity of reaction. Okay, so next one is kinetic stability. This type of stability deals with the rate of reactions of complexes in solution. Okay, this type of stability deals with the rate of reactions of complexes in solution. It refers to the speed with which the transformations leading to equilibrium will occur. It refers to the speed with which the transformation leading to equilibrium will occur. But as per Tobe, the mechanism of chemical reaction, formation of intermediate, Tobe has classified a complexes into labile and inert complexes. Tobe has classified a complexes into labile and inert complexes. So let's see labile and inert complexes. So before start our topic, one thing is very important, or remember a very easiest trick. Labile means easily exchangeable and inert means slowly exchangeable. Okay, only remember these two words. Labile means easily exchangeable and inert means slowly exchangeable. So the complexes which rapidly exchange their ligands with other species are called as labile. The complexes which rapidly exchange their ligands with other species or other ligand are called as labile complexes, and if complexes which slowly exchange their ligands then they are called as inert complexes. Or in another word, if ligand is easily exchangeable with another ligand, is called as labile ligand, and if ligand is slowly exchangeable with another ligand, that ligand is called as inert ligand. Okay, this was about labile and inert complexes. But according to Henry Tobe, the labile is nothing but if reaction having half-life of reaction is less than 30 seconds. Labile complexes are nothing but if reaction having half-life, that is T half, is less than 30 seconds, that complexes are called as labile complexes. Or if reaction having half-life is greater than 30 seconds, that that complexes are called as inert complexes. In simple language, T 1/2 is less than 30 seconds, that complex are labile complexes, and if T half is greater than 30 seconds, that complex are inert complexes. Okay, I again repeat, what is labile complexes? The complexes which rapidly exchange their ligands with other species or with other ligand are called as labile ligand, and the complexes which slowly exchange their ligands with other species or other ligand are called as inert complexes. Okay, so let's see explanation for labile and inert complexes. So see, here is vanadium complex which having charge is +3. So here oxidation state for vanadium is +3. As we know that atomic number for vanadium is 23, means its electronic configuration is 3d3 4s2, but as it carries +3 oxidation state, its valence electronic configuration is 4s0 3d2. So there are d2 system for this complex. Obviously there are only 2 electrons in d orbital. So let's see, here is d orbital, here is s orbital, and here is p orbital. As the system contains d2 electron, that is 2 electrons only, so this is T2g. Yellow color shows T2g orbital, while this blue color shows EG orbital. In T2g there are 2 electrons, 1 and 2. 1 is vacant. Okay, so it is vacancy for entering nucleophile or entering ligand. So let's move towards next complex, that is COCN6-3. So as cobalt has 27 atomic number, means its electronic configuration is 3d7 4s2. But as it carries +3 oxidation state, so the system comes d6 system. So obviously there are 6 electrons in d orbital. So here is d orbital, here is again s orbital, and here is p orbital. So as we know that CN, that is cyanide, is strong field ligand, all ligands are first paired. So T2g orbitals are completely filled here. Okay, and next one is MnCl6-3. System carries d4. So the system is d4, and d orbital contains 4 electron, and as Cl is weak field ligand, so the distribution of electron is like this. In T2g there are 3 electron and another electron goes to Eg orbital. So 1, 2, 3 and 4. Okay, so as per Tobe suggested that if your T2g orbital contains 0 electron, means no electron, 1 electron or 2 electron, there are vacancy for entering nucleophile or entering ligand. So that time that complex is labile complexes. Means if your system contains 0 electron, 1 electron or 2 electron in T2g orbital, so your complex must be labile complex. Okay, but If your T2G orbital is fulfilled, that time your complex is inert complexes. So in next slide we will see examples. So here are all examples. Start from D0 to D10. So let's see D0, it is labile. As I have already told you that if your system contains D0, there are chance for entering ligand, so it must be labile complex. If system contains D1, obviously there is only one electron in T2G orbital, so again it will be labile. If system contains 2, T2G orbital contains 2 electron, again it will be labile. But if your system contains 3 electrons, that is D3 system, 3 electrons are filled in T2G, that is T2G3 EG0, that time there is no vacancy for entering nucleophile or entering ligand, so that complex is inert complexes. Okay, let's move towards high spin and low spin. What is meant by high spin? High spin are nothing but weak field, means there is no pairing, and in low spin or strong field there is pairing. In D4 system, while there are 4 electrons in your system, 3 in T2G and 1 in EG, so that time is labile. Let's see previous example. See, this is labile one because system carries 4 electron, 1, 2, 3, 4. That time your complex is labile one. But in case of strong field, that is low spin complexes, all 4 electrons are in T2G, so your complex is inert. These are the examples for all these complexes. In case of D5, it is labile when your system is high spin. When your system contains weak field ligand, that is labile one. That complexes is labile one. But in case of strong field ligand, that complex again is inert. In D6 inert, D6 high spin as well as low spin. Both system is inert one, and for D7, D8, D9, D10 are labile one. Why this is so, we will discuss in next slide as per VBT. Okay. So here explanation of liability and inertness according to VBT. VBT describes octahedral complexes into two types: inner orbital complexes, that is D2sp3, and outer orbital complexes sp3d2. Let's see inner orbital complexes. These complexes have D2sp3 hybridization. As name indicate that inner orbital complexes. So D2sp3, D2 is at inner side, so it is called as inner orbital complexes. The hybrid orbitals are filled with ligand, electrons, and T2G orbitals of metal accommodate the d electrons of the metal. What happened in case of D2sp3 hybridization? What happened in case of D2sp3 hybridization? The hybrid orbitals are filled with ligand electrons, and T2G orbitals of metal accommodate the d electrons of the metal. Outer orbital complexes, these complexes have sp3d2 hybridization. In these cases, the bonds are weaker as per VBT, so they are generally labile. Okay, sp3d2 outer orbital, as d2 is at the outer side, so it is called as outer orbital complexes. In case of sp3d2 hybridization or outer orbital complexes, VBT, as per VBT, the bonds are weaker, so that complexes are generally labile one. Okay, let's see example. Mn2, Fe2, Fe3, all are the labile complexes. Means student, consider if your system carries D0, D1, D2 electrons, And if hybridization of complexes are outer, that is sp3d2 hybridization, that time the complexes must be labile complexes. But if your system possesses inner orbital complexes, that is d2 sp3 hybridization, and system carries 3 or more than 3 electrons, that time the complex must be inert complexes. Okay. In short, if T2G levels are left vacant, means there is vacancy for incoming nucleophile or incoming ligand, then the complexes can associated with incoming ligand, and so the complex is labile one. And if all T2G levels are filled by electrons, then the complex is inert one. So student, let's see factors affecting liability of complexes. So first factor is size of central metal ion. Consider if your size of your central metal ion is small, so greater will be the inertness and lesser will be the liability. Why this is so? Because if central metal ion has smaller size, so it is highly or tightly bonded with ligands, so that ligand is unable to replace easily, so obviously there is greater inertness and lesser will be the liability. Okay, so second factor is charge on central metal ion. If your central metal ion carries greater charge or higher charge, greater will be the inertness. Again same concept is here. If your central metal ion has greater charge, greater will be the inertness. Why this is so? Because if your central metal atom has greater charge, obviously it is electron deficient, means it is strongly bonded with its ligand. So again there is replacement of ligand is very slowly. So obviously greater will be the inertness and lesser will be the liability. Third factor is d electron configuration. If electrons are present in antibonding, that is Eg star orbitals, the complex will be liable. The ligand will be weakly bonded to the metal and hence can be substituted easily. Means if complex is more liable, it is less inert one. Okay. Complex with empty T2G orbitals will be liable because ligands can approach easily without much repulsion, as we have already discussed about that. In short, if the complex contains less than 3d electrons, it will be the liable, or if one or more Eg star electrons or electrons in antibonding orbital are present, it will be labile one. Okay, and last factor is geometry of complexes. 4 coordinated complexes are more labile than 6 coordinated complexes. This was about factors affecting on liability of complexes. What was that factor? Size of central metal ion. After that, charge on central metal ion. Third one is d electronic configuration and geometry of the complexes. Okay, student. So explanation of liability and inertness according to CFT. This explanation is not much important, but see, if CFSE value increases by association or dissociation of ligands, that complexes are said to be labile complexes. What I have told just, if CFSE value increases by association or dissociation of ligands, that complexes are said to be labile complexes, and if CFSE value decreases by association or dissociation of ligands, that complexes are said to be inert complexes. Okay, so let's move towards last topic, that is stability constant or formation constant. See, the formation of complex in aqueous solution proceed through a stepwise manner with corresponding equilibrium constant. Let's see, M plus L gives Ml, Ml plus L gives Ml2, Ml2 plus L gives Ml3. Okay. C, K1, K2 and K3 are constant for this reaction. So rate of reaction is equal to K1 is equal to Ml upon Ml. For K2, for this reaction, the rate of reaction is Ml2, Ml and L. Again for rate for third reaction, K3 is equal to Ml2, Ml2, L. Okay, these K1, K2 and K3 and K1, Kn are called stepwise formation constant. So overall stability constant is M plus Nl gives Mln. Okay, this is nothing but a stability constant for your complexes. Okay, stepwise formation constant. Okay, student. So in today's lecture, we have discussed stability of complexes. After that, thermodynamic and kinetic stability. Next, inert and labile complexes. After that, stability constant. So student, here we have finished our today's topic.